Hello everyone, welcome to AstroTalks Quarantine Talk series. My name is Tutku Kolcu, and I'm a recent graduate of University of Birmingham, and I'll soon be joining Astrophysics Research Institute of the Liverpool Jonesmore University. I am also the former president of AstroTalks, so it is my absolute pleasure here today to welcome all the new students to our university and also to welcome astronomy enthusiasts who are joining this session today. So thank you all for being here, and before we run out of time, let me run you through with my plan of today. So I'm going to start with introducing the beautiful device of Spitzer, as you might have guessed from my talk title. And later on I'm going to talk about why multivalent astronomy is important, basically why it's important to observe different types of radiation coming from the universe. And I'm going to specifically focus on the infrared range, since Spitzer is an infrared telescope. I'm going to describe how and where exactly the infrared radiation is coming from out of the universe, and what type of instruments Spitzer have in order to be sensitive towards this radiation. And later on I'm going to describe the structure of Spitzer, so its technical design and its orbital trajectory, and I'll basically mention of the advantages provided by its orbit and technical design for its results. And Spitzer was out there for a very long time, so it had different missions going on, and I'm going to talk about these missions. And later on, hopefully, I'm going to show you some very pretty pictures to keep you motivated towards the end of my talk under the discovery session. So, and I guess you will all join me with me and the committee members, of course, with the Q&A session after the talk. I'm very looking forward to hear your questions about it. Okay, so let's get started. So, in my personal opinion, Spitzer was one of the most popular and powerful instruments that have been sent to space within this past 20 years. It was there for a very long time, observing the infrared radiation coming from the universe. So, in fact, it launched in late August 2003 and it commissioned in late January 2020. So, there is roughly a 16 years old time that Spitzer was out there looking for infrared radiation coming from our universe. Actually, it wasn't the first or only space telescope that is infrared sensitive. However, it was the most sensitive at highest resolution of its time, basically. So it was one of the telescopes of NASA's Great Observatories program, which this program primarily focuses on multivalent astronomy. So basically primarily focuses on learning about the universe in a fuller way by sending telescopes out there that are sensitive to different types of radiation. For example, we have the famous Hubble Space Telescope as a part of this program, which is looking for visible light. We have Spitzer, which we'll learn a bit more in a bit. We have Chandra as an X-ray observatory, and we have Compton as a gamma-ray observatory. And why people are investing so much time and money for these instruments, I can hopefully describe you with an example here. So, why multivalent astronomy is important? So this is the image of Milky Way, and each horizontal image here is the same target and observed with different telescopes. So basically, at the top we have the radio continuum, and you can see there is more radio emissions coming from the central part of the galaxy. Galaxy is this really, and that's coming from the scattered electrons from interstellar plasma. And then we have atomic hydrogen coming from diffused gas. And moving down a little bit, we have molecular hydrogen, which is coming from more condensed, more compact molecular clouds, which are in fact the birthplace of young stars. Moving down a little bit, we have infrared radiation coming from the dust heated up by starlight or planetary light or comet light. In general, heated up dust radiates in infrared, glows in infrared, which I'll talk in a bit about different ranges of infrared anyways. So moving down a little bit more, we have the optical range, and now you can see dark patches here, which is actually dust blocking the majority of the visible light coming behind it. And moving down, we have even hotter shocked gas with X-ray emissions, and you can see the cosmic rays and atomic nuclei, gamma emissions coming from these cosmic rays and atomic nuclei. So as you can see in this image, And each part of this image gives us something unique, teaches us something different. This is why people are investing so much time, money, and effort in this. Because if we're observing a target with different wavelengths, this means that we understand our true face of our target in a bit more fuller and a clearer way. So this is how. This is why multi-wavelength astronomy is very important for scientists. Okay, moving to our traditional electromagnetic spectrum here, I want to show you we have radio waves which have longer wavelengths and shorter frequencies, lower frequencies, and we have all the way up to the spectrum. We have gamma rays at the end with high energies, higher frequencies, and shorter wavelengths. And you can see some of this radiation can penetrate Earth while some cannot. For example, majority part of the infrared cannot penetrate Earth. UV, X-ray, and gamma rays cannot penetrate Earth for our sakes because they're very dangerous for us. So basically our atmosphere is blocking these type of radiation. So this means if you have ground-based observatories trying to capture this radiation coming from the universe, you cannot. Actually, this is the main reason why people are sending telescopes out into space. Basically, by doing that, they eliminate the atmosphere from their equation, and they can reach to radiation coming from that parts of the spectrum. In fact, actually, I want to show you the infrared part, actually, which is close to the visible light, is in this gray area, which I think this means that it depends where your ground-based telescope is located at in general to capture this near-infrared light. For example, if you're in Cyprus, which is where I am currently, you're probably not lucky to observe near-infrared radiation because of humidity. But if you're in Chile or Hawaii, you're more likely to observe it. And one more thing that I want to mention in this picture is the temperature scale. So if I'm being rough, the infrared radiation starts from roughly 5 Kelvin, which corresponds to negative 286-ish degrees Celsius. So that means anything higher than this temperature will be radiant in infrared. And if I put a maximum, let's say 3000 degrees Celsius for this range, which corresponds to roughly here, this means that we have a very big temperature range for infrared. So this means that from very distant cold objects to very close hotter objects, we have a very wide range of area that Spitzer can be a use. So Spitzer can help scientists to understand. This is, I think, one of the main reasons why Spitzer was very popular and they kept it going for all these years. Okay, so focusing on the infrarange a little bit more, I'll drag my window down. Yeah. So as I said, we have different ranges of infrared. So we have near, middle, and far infrared ranges of the infrared spectrum. So near infrared is the part where it sometimes might be observable from the ground. For example, we have Vista Observatory in Chile, and we have UCURT in Hawaii. So these are near infrared sensitive ground telescopes, and they are lucky to observe this radiation. However, Spitzer is more in the middle to far infrared region. So near infrared is coming from hotter objects, relatively hotter objects. For example, from 500 degrees Celsius to 3000 degrees Celsius. It corresponds to the near infrared region. And then we have the middle infrared region, which is primarily the dust which is coming from primarily heated up dust. So dust can be heated up by starlight, protoplanetary disks, planets really. So anything basically that heats up the dust, the heated dust basically glows in infrared. And then later on we have the further colder objects corresponding to far infrared region, and the far infrared region roughly corresponds to negative 286 degrees Celsius to negative 130 degrees Celsius-ish. So as you can see, far infrared is very different than near infrared region objects. However, this is not a problem for Spitzer because it has 3 different instruments that are sensitive to different regions. For example, we have the infrared array camera IRAC, which is in the beginning of the middle infrared region. We have infrared spectrograph, in this middle regions as well, and beginning of the far. And then we have multi-imaging photometry on Spitzer telescope, which is basically, as I said before, from colder to hot, we have a far range that Spitzer is capable of observing. Okay, so let's move to the technical details of the Spitzer telescope a little bit. So I am no telescope expert, if I'm being honest. However, I'm going to describe this in a quite concise way in a way that I also understand. So the scientists divide design of the Spitzer into two: the cryogenic part, the cryogenic assembly, which consists of the 85 centimeter telescope itself, and the three other instruments that I've mentioned: IRAC, IRS, and the MINS. And that's basically it for the first part. And later on, we have the spacecraft part, which is basically the main part that connects the telescope to Earth and basically also the power of the telescope. So we have the sonar panels, which they are usually faced towards the sun in order to power the instrument. And you have the high gain and low gain antennas, which are the parts which is pointed towards the Earth to prevent the communication with the Earth. And this is basically, I think, it. There is also an outer shade coated with matte black color in order to minimize the heat absorption of the telescope. Another main advantage of Spitzer telescope is actually its orbit. So Spitzer was the first telescope actually sent to an Earth trailing trajectory, which means that it literally trails the Earth and orbits around the Sun. So that actually gave Spitzer a naturally cooler environment because it was away from the Earth's radiation itself. It was naturally cooler, so there wasn't anything blocking its way out as well. So it had also a wider field of view, wider sky area that a Spitzer could really observe. For example, Hubble Space Telescope is a lower orbit telescope, and time to time the Earth can block its view when it's capturing something. But it's not the case for Spitzer, so which was one of the main advantages as well. Being a cryogenic satellite, Spitzer also contained liquid helium in order to keep the telescope at negative 260-ish degrees Celsius. If I'm being more exact, roughly 5 Kelvin. And that was actually crucial for far-infrared observations, which actually the cold mission of the Spitzer here is sensitive to. So let's speak about the missions a little bit. Okay, yeah. So, a few months after its launch, Spitzer started its observations, which scientists called it cold mission. So it was basically sensitive to 5 Kelvin degrees temperatures, and it was able to capture middle to infrared regions of the infrared spectrum. It was able to use all three of its instruments, IRAC, IRS, and MIMS. However, what happened is that in 2009, the helium supply finally ran out, and actually the cold mission itself was aimed to last roughly about 2.5 years, and the device being very efficient and having innovative cooling because of its orbit, it lasted roughly about 5.5 years instead, so that was even beyond expectations. And coming towards the warm again, in 2009 the Spitzer ran out of its helium supply, and therefore it started to gain more temperature a little bit, which is still pretty chilly. So it raised towards 30 Kelvin, which corresponds to negative 243 degrees Celsius. However, this was only enough for middle infrared regions because we have lost our far infrared glasses with this temperature. So the Spitzer stayed out there for roughly roughly sort of 10-ish, 9-ish more years. However, what happened in 2016 was, so because of its orbit, as it orbits around the sun, sort of Spitzer gets drifted away from the Earth, so the scientists have to sort of tilt its angle to a higher angles in order to keep communication going with the Earth. But if they tilt the Spitzer angles, that means that the solar panels are sort of facing far further away from the sun, and that sort of puts more stress to the puts more stress onto the battery of the instrument itself. Also, it makes it exposed to more radiation coming from the sun. So this was sort of in a more riskier mode for Spitzer. And there were other missions that were needed to be funded by NASA, so they thought to shut down Spitzer in 2016. However, fortunately for Spitzer, what happened was the mission which was supposed to replace Spitzer, which I will talk in my very last slide, sort of got delayed until 2021. So they thought, okay, so let's keep Spitzer in this riskier mood, the riskier session, and let's continue its observations until this new mission, this new instrument is being launched. And then they called from 2016 to 2020 part Spitzer Beyond, which is, I think, an appropriate name for it, because the Spitzer even achieved more than the expectations. The whole mission was an absolute success, so I think that it deserved basically the Spitzer Beyond name was, I think, very well deserved. Okay, so coming to the discoveries of Spitzer, of course I'm starting with exoplanets. So Spitzer was quite a powerful telescope for exoplanetary science, actually, because it had very advanced star trailing systems that could find stellar systems, and it was also had quite an advanced way of dealing with temperature variations, which made it an ideal telescope for exoplanet science. And exoplanets are, I think, one of the most popular research fields for the past decade, for the past 20 years as well. And there were so many telescopes out there pointing towards characterizing exoplanets and discovering exoplanets, like TESS, Kepler. TESS is a relatively new one. However, Spitzer was actually the first telescope which directly captured light from exoplanets. So before Spitzer's discovery, all the exoplanetary science, all the exoplanetary discoveries have been done by indirect measurements, indirect methods. For example, the transit method, as I'm showing it here. So as an exoplanet transits around its star, and as it blocks the light from its star, we can see the brightness change in its spectrum. And by measuring this brightness change, before and after as well, we can basically characterize our exoplanets. But this is sort of an indirect method. And instead what Spitzer observed was literally the infrared glowing of the planet. So by capturing the star plus planet system, and only the star as the planet is transiting around the star, they could basically isolate the planet spectrum only. And this was sort of a revolutionizing way, because that was the first direct capture of the exoplanets. And it's not surprising that Spitzer sort of achieved that anyway. Continuing with exoplanet hunting, Spitzer was one of the telescopes within the collaboration of discovering the TRAPPIST-1 system. So the TRAPPIST telescope found the 3 of the exoplanets of the system, and then the ground collaboration with the ground-based and Spitzer, they confirmed the existence of these 3 exoplanets. And also with this collaboration, Spitzer also helped discovering 4 additional planets to the system as well. So what's special with this system is all 7 planets are possibly to contain liquid water. And this is a very big breakthrough for the past years. And 3 of these planets were in the habitable zone, which will be soon, with the new upcoming mission, which will be soon characterized a little bit further with the new missions coming out. But this is also not surprising that Spitzer had a part in this, because it's very powerful. Continuing with exoplanets, as I said, that Spitzer was quite sensitive to temperature variations. It has produced the first ever exoplanet weather map. So what scientists have done that, basically this exoplanet is an illustration, by the way, this is not a real image. So the Spitzer discovered another hot Jupiter as it did with the direct captures, and scientists realized that after capturing the exoplanet weather map of this new exoplanet, they discovered that the exoplanet is actually tidally bound to its star, so it's more like our moon. basically. So it only shows one face to its sun, and its one face is darker. So this initially gives you an idea that one face should be hotter than the other face. However, with this weather map, they sort of discovered that there is a very little temperature variations all over its surface. And by doing that, they actually characterized that this new exoplanet has very drastic winds that sort of spreads the heat from one side to the other side. And I think this is a very pretty cool discovery as well, characterizing the atmospheres of the planets. Okay, so continuing with planets, we have our favorite planet of everyone, Saturn, with its pretty icy dusty rings. So what happened here was, as Spitzer was enjoying its view towards Saturn, scientists discovered an infrared glow coming from the ecliptic plane of the Saturn itself. And soon after discovering this glow, they actually realized that this is a further extended ring of Saturn. And that was basically a secret by then, because the ring was discovered to be made of mainly dust, which reflects very little sunlight. Not sunlight, it reflects very little visible light, basically. So that's basically why it has kept a secret for all these years. And after doing some more research, they have actually realized that it's more likely that this dust ring made up of one of the moons of the Saturn called Phoebe, as you see here. Yeah, so they called it a Phoebe ring. So how this formed was theorized by just basically looking through the structure of the Phoebe itself. So as you can see, it has a quite cratered area, quite cratered surface, and they have realized it's probably the dust ring was made up as a result of the impacts on the surface of the Phoebe, and which makes these craters and reveals quite a lot of dust from the surface of the planet. And as it orbits, which the dust ring was more lined up with the Phoebe's orbits anyway, it also creates this dust ring as the Phoebe orbits, and sort of diffuses the dust particles to the environment. However, another important discovery after this was actually coming for the other moon of this, another moon of Saturn, Iapetus. So starting from Cassini's age, no one actually figured out why this Iapetus moon has this mysterious dark side, because there wasn't any evidence of this material in this Saturnian system. And they have actually realized that after discovering this dust ring, they have realized this dark material of Iapetus is actually it's the same material with the dust ring, and they have theorized that it's probably that this dust ring was a little bit more wider in diameter, and Iapetus probably swept some of the material as it orbits. So after discovering this dust ring with Spitzer, basically they have also solved a 200 years old mystery with Iapetus, which I thought it was pretty cool. Okay, so continuing with the galaxy part of the discoveries, because I am a galaxy person. In fact, it's my it's much close to my personal interests for research. We have our artistic impression of Milky Way here. However, before Spitzer, scientists actually thought Milky Way has 4 major arms. So looking to the Hubble tuning fork of galaxy classification down here, we have different types of galaxies. So we have ellipticals. They also can characterize with respect to their increased ellipticity. We have S-Naught galaxies, which are lenticulars, which is in between ellipticals and spirals. And then we have our spiral galaxies classified as barred and unbarred spiral structures. And there also can be differ based on their decreased bulk size and arm openness angle. So before Spitzer's observations, as I said, the scientists thought actually Milky Way has 4 major arms without a bar structure in the middle. However, after 400 hours-ish, dedicated to exploring the Milky Way, with Spitzer, they have actually realized that two of the arms are actually consist of more denser material and consisting of more younger and older star regions. And two of the arms are actually only made up of dust and with some pockets of a star-forming region as well. So they have realized there is only 2 minor and 2 major arms instead of 4 major arms for the Milky Way. And they have also realized that there is an extended bar structure of its bulge after Spitzer's discovery. Therefore, with Spitzer's discovery, the Milky Way actually gained a whole brand new classification based on Hubble scheme. So I thought that was also pretty cool. Moreover, even before Spitzer launched, there was this GLIMS project, which is focusing on characterizing the inner structure of Milky Way. And what Spitzer did was, throughout 10 years, it captured the Milky Way with Spitzer observations, observed Milky Way in 3 different cameras, which is in fact the color composite image here. And this image here is made up of roughly 1 million snapshots stitched together to produce the first wide field image of the Milky Way galaxy. And this was actually the first panoramic image, basically, of the galaxy itself. And to do that, it took Spitzer 10 years and roughly 2 million snapshots in order to build this beautiful creature here to help the GLIMS project. Okay, I just here want to highlight another galaxy view with the infrared radiation of Spitzer. You can see here this is the Andromeda galaxy, which is our nearest neighbor, and you can see behind the dusts heated up. I'm basically here highlighting how the galaxies are actually can be visualized with infrared radiation. So you can see here all the dust being heated up, which you cannot actually see the same structure here with the visible light. And I think this is quite an enjoyable view. So because Andromeda is quite close, it took Spitzer to actually sort of stitch roughly 11,000 snapshots in order to produce this beautiful image here. Okay, so continuing with molecular clouds. So molecular clouds are actually the place of places that have the star-forming regions. So this is a dark nebula row of, and in fact in visible light it's not too much information revealed. And however, here this is a Spitzer image, actually a color composite image made from all 3 cameras of the Spitzer. And by using Spitzer's observations, scientists actually discovered more than 300 young stellar objects shining within this beautiful dark nebula. And the different colors here represents different temperatures. We have the red colors coming from younger stars, we have the old colors coming from older stars, and all the green color actually indicates the colder gas diffusing regions. And I think this was also pretty important that they have discovered that this dark nebula is actually a stellar nursery where young stars are being born. And Spitzer helped for it. One more thing about Spitzer discovery is the double helix nebula. So it's you can actually see the shape of it here, that twisted spiraling shape. And scientists so basically Spitzer discovered this nebula which was very close to the galaxy's center, and scientists took this as an evidence of gas spiraling around very magnetic field of the supermassive black hole, as it sort of is more diffused in the galactic center. So this was sort of the first evidence of this. Not first evidence, but this was sort of an evidence of this theory that there is strong magnetic fields around the galactic center due to the supermassive black hole might be there. Okay, and finally, I want to talk about the near-Earth asteroids, which is sort of the closer objects to the Earth rather than all these distant objects that I've just talked about. So the near-Earth asteroids are basically asteroids that are sort of coming closer to the Earth's orbit, and NASA is trying to sort of prevent them colliding with our Earth. And they are quite hard to be detected and characterized with visible or optical telescopes because they do not radiate any light. They do not radiate any light, so it's quite harder to use visible light range in order to characterize them. However, they have some temperature, which is definitely higher than 5 Kelvin, and therefore the Spitzer is an ideal telescope to characterize them because they do glow in infrared, which actually Spitzer have done characterized dozens of them anyway. So this, by showing you this, I just actually want to conclude my slides because basically I'm trying to make this conclusion that from very far distant objects to near-Earth asteroids, Spitzer had a very wide range of research areas that could be studied with observations. And I think it is time to appreciate this beautiful device and its results, since it came to an end earlier in this year. So what next is the James Webb Space Telescope, really? So it is again an infrared sensitive telescope, which will be sent, which is aiming to be sent in 2021 out in space. And its primary mission will be focusing on exoplanet discoveries and specifically characterizing the atmospheres of exoplanets. And no doubt it probably will start the TRAPPIST-1 system that I have shown. And yes, this was actually the delayed mission that I have talked before, Spitzer Beyond mission. And I hope all the best for this James Webb Telescope. And I'm sure it's going to revolutionize the discoveries, new discoveries that Spitzer couldn't really find out, if there is any. Well, thank you very much everyone for listening my talk. And I also would like to thank you, Astro Subcommittee, for hosting me here today as the guest speaker. And I'm looking forward to hear your questions later on. Once again, thank you very much and keep safe.
Right. Hello, everybody, and welcome. It is great to see you come to join us again. And we are absolutely delighted to welcome last year's chair, Toots, into the Q&A session. We wish to thank her very much for her talk. It looks like we already have a couple of questions about the talk, so this is going to be really, really good. And as always, if you have any other questions, please type them in the chat or come and join the Zoom Q&A session directly and ask your questions there. So without any further ado, we'll start with the first question that was posted in the chat, which was, can Spitzer discover comets as well?
So hello everyone, thank you for joining again. So before we run out of time, I want to start answering the questions as well. So in fact, I did include some comet examples in the discovery session, and then I decided that I will talk forever if I keep putting these on. So I did remove it. I wish I actually put it. So yes is the answer. Actually, Spitzer did in the past discover dozens of comets, or sort of discovered objects that were classified as asteroids, and then they turned out to be comets. So those type of discoveries were actually amongst Spitzer discoveries. One was that was the example I was going to put in, was about a comet in Jupiter's system that suddenly got exploded, and then Spitzer obviously solved that. So by capturing the high contrast image within the infrared instruments from Spitzer, they seen that the comet itself is actually showing some filaments in the middle, and then they could basically observe the whole structure of the comet to hunt an explanation why the explosion happened, which I believe they couldn't find an explosion. But I don't know if they have focused later on for this discovery. But basically, yes, Spitzer can discover comets, is my final answer.
Brilliant, thank you very much, Toots. The second question is, in your multi-wavelength image of the Milky Way, there was 2 radio continuum images. What are the differences between these emissions, and where are they coming from within our universe?
So basically, I did skip the second radio continuum on purpose, actually. So just to make it clear, so basically radio emissions are coming from a high energy electrons being scattered within intense magnetic fields in interstellar plasma. And basically in both images, the frequency range was different. And one had a better resolution than the other one. Basically, the one I skipped did have much more details on it, actually. So I wanted to like sort of skip it and just briefly mention before, like to not make it too much long, basically. The difference between two images is also they've been captured by different observatories. So the first one was, I think, if I remember correctly, was a Jodrell Bank image, which is a radio observatory in the UK. And I can't really remember what was the second image taken from. But basically, different observatories gives us different resolutions. And the second, the high frequency image basically was showing much more details, and it was more, it was a better image basically, but I did skip it. But the origin of the radio emissions are actually the same thing. There was just a bit much details in the second image basically.
Thank you very much. I think that hopefully answers the question. I can't see any other questions on the chat at the moment, and there don't appear to be any other questions in the Zoom Q&A session either. So I'm going to ask a very quick question. Obviously, you know, we have some fantastic space-based telescopes that really seem to, at the moment, span a whole range of the electromagnetic spectrum. When we're now combining this with gravitational waves, just how exciting is it to be working in the field of astronomy? You know, both studying at an undergraduate level and then going on to do postgraduate study with such amazing technology available now.
Well, it is definitely very exciting. So if I start from the beginning, actually, I wasn't going for astronomy at the beginning of my physics degree. And then after seeing all these beautiful discoveries, especially being in Birmingham, which they had a very active gravitational waves group, I definitely immediately changed my degree from physics to astrophysics, because I was like, okay, I have to go towards this way, because it was very exciting for me. And as you said, every day they build up with the build-up technology. They sort of it gets even better and better. And you can't even see that my voice is shaking with the excitement in it. So I am more in the galaxy evolution side, which in that field as well, there is so much going on. I can say the popular field is currently now exoplanets and gravitational waves, really. But yeah, it's very exciting to see these people are putting so much effort towards their science, and I'm actually proud to be a part of this as well.
Perfect. That's really exciting to notice, and I'm sure it's going to inspire several other students to, pursue physics and astrophysics in the future as well.
Well, you guys are also inspiring everyone. I would say, coming up with the quarantine talks was a very great idea, I believe. So, in this literally lockdown term, everyone was, I'm sure, very glad to see these type of talks going around, especially that sort of coming from student societies as well. I think that's quite precious.
Thank you very much
for organizing it.
While we wait for some other questions, I have a question of my own that I would like to ask. I'm on the particle physics and cosmology course, so it's while going through your talk, inevitably I ended up thinking about the applications of infrared astronomy in cosmology. Mm-hmm. And although as you mentioned, the range for Spitzer, in the cold range for Spitzer is from 5 Kelvin and above, I was just wondering, could infrared astronomy or Spitzer effectively have been used for cosmology applications such as detecting cosmic microwave background or other telltale signs of the Big Bang?
I don't think they would use it for cosmic microwave background. And I'm sorry, I can't really think of an application that I came across related to cosmology side. There was quite a lot of observational astronomy research field based with Spitzer's infrared glasses. But I can't really remember seeing a specifically like focusing on the cosmology part. I might be mistaken, actually. There might be an infrared scientist like shouting from the like outside window towards me, but yeah, I can't really think of something.
No worries, that's perfectly fine. And I have another question as well, if that's all right, if we're okay with time, Luke?
Yeah.
Perfect. Are there any objects in the universe that would only be visible in the infrared region? So if there would be no other telltale signs with, let's say, X-ray astronomy or just visible range astronomy, but only in the infrared spectrum we can detect these objects.
I see. I don't think so, but I can tell you that, for example, the dust I've talked about is quite, for example, the dust ring of Saturn sort of remained hidden for like all these years from Cassini's years, all the way up to the Spitzer's discovery. So there are stuff that are not invisible, but it depends if you're looking towards that direction, basically, because universe is obviously very big. And I can tell you there are some invisible stuff that we couldn't really discover them yet. And sort of infrared is sort of the key because it's sort of a good temperature range that can be that can be basically discovered. That's why basically, for example, dust is in infrared glow. So from the with visible light, basically the things that are invisible can be basically studied with infrared. And if you don't really see them, I believe you don't really go and scan the sky with X-ray telescopes, for example. So if you sort of start viewing your target with infrared, you can then basically focus on that object with other telescopes as well in order to observe it. But I don't think there is one thing that only is infrared glow.
Perfect. So after Spitzer was decommissioned, what happened to it effectively? Has there been a re-entry or is it still out there?
So basically, it is actually still out there. So what happened was, after like basically downloading the final data set of it, they sort of send a command basically putting it in a sort of hibernation mode. So basically in a safe mode. So it stayed there pointing its solar panels towards the sun. So it stayed there. And if you remember from my talk, I said it starts getting drifted away from the Earth. So at some point, this distance will sort of reach to a maximum distance, and then Earth will start to catch up, and then it will direct the Spitzer to its orbit back, and then it will get closer to the sun. It will speed the Spitzer up, and then the Spitzer will pass towards the Earth, and then that's sort of going to be in like on and off stage of like that. However, this is not going to be like for a very long time because that's probably going to be like 2060s or something in general. But yeah, so it's actually good to know that Spitzer will be out there unless someone actually decides to take it back to Earth to put it in a space museum or something, which they can do. So until then, Spitzer will be out there like sleeping, waiting for the next command, basically, which will never come. Unfortunately.
So I guess to pose a very challenging question to you, obviously yourself as a scientist and us as undergraduate students that are interested in this sort of field, being able to send space-based missions and telescopes up there to do this vital work that we can't do from the ground is incredibly important. However, as you've kind of alluded to, it then leaves a large amount of space debris, space junk up in the Earth's atmosphere, which may actually, or in low Earth orbit, which could in future inhibit our ability to either leave Earth or send future missions up. Kind of, how do you sort of look at the idea of balancing this thing? How many spacecraft do you think we should be sending up, and what do you think about some of the small or the large even constellations, stuff like Starlink, that are being sent up, and how might that interfere with some of these big telescopes that we might send up in the future?
Well, I would probably be cruel to say, like, don't send any telescopes up, especially if I'm going to work with a few of them in the future. But I see your point of view, but like these type of things, if it gets quite excessive, that's going to cause problems like space junk. And currently, I'm not actually currently sure what's the level of the junk currently for Earth. I think it's not like quite critical yet. But I don't know. I believe it's sort of a must for us to sort of send these type of things currently in order to still develop our understanding. Well, yeah. Brilliant. So I'm not in the team, I'm not in the team against these type of things yet.
Thank you very much. Yeah, it's obviously it is a very tough question, and we've got a balance between developing our scientific understanding, obviously having everything needed for modern life, so the satellites that help us back here on Earth, and then preserving our environment. So yeah, it is
definitely because in order to learn more about the universe, to develop even understanding even further, we definitely need these space junk material telescopes. So yeah, it is sort of a hard balance to keep these going or not going. It's a quite tough line, basically, if you want to cross or not. So I'm not crossing yet.
Can I take this opportunity just as a shout out to some upcoming events that AstroSoc will be conducting in October? So we have World Space Week coming up in October, and the theme for World Space Week 2020 is Satellites Improve Life. So there's going to be loads of talks and other interactive events where we're going to talk more about, satellites, how they impact our lives positively and perhaps even negatively, so that we get a balanced view of it. And this is probably going to be something that we're going to touch on quite a bit.
Sounds fantastic.
So I think this is kind of drawing the Q&A session to a natural close. Obviously, we've just heard from Anwesha about some future upcoming events. So keep your eyes and ears both on the email system and on our social media for more information about those. I'd like to thank Toots on behalf of AstroSoc once again for delivering this talk and for being here to answer the questions on the Q&A. And hope you can all join us next week.
Thank you very much for hosting this session and hosting me as a guest speaker as well.
Thanks, Toots.
Thank you.
Thank you, everybody, and goodbye.
Bye.